So I'm going to go through this homework assignment, which has mostly to do with limits, and explain where you can find the material in the book to do the problem and maybe help with the problem a little bit in some cases. And I'm sorry about the noise from the rain. There's a hurricane hitting right now. For this first problem, we've done a lot of stuff like this. This is basically just computing the slope of the secant line. And the section of the book where that happens, this is Calculus Volume 1 on OpenStax. And if you look in the chapter Preview the Calculus and look at the stuff on the average rate of change, then that part of the book tells you how to do this problem. Excuse me. So let's go on to the next thing. So let's do this. For graphing, I suggest Desmos. So let's go to desmos.com and plot this function. And the homework assignment, they call the variable theta, but we can call it x. And so you should look on this graph and try to guess what is the limit as x goes to 0 from this picture. So if you don't have any idea how to do that, then you should read the section of the book on limits. Okay, so this says determine the limit as x goes to 3, and again, just the section of the book on limits explains how to do that. Alright, so this one is introducing some material that we haven't talked about in class yet, namely one-sided limits. So we might as well explain this idea with this problem. So look at this notation that they're using. The limit as x goes to -1 minus. So that means from the side of the negatives. Let me give another example here. So here are some axes, and let's say that we have a function that looks kind of like this. And let's say that this is x equals 1, and this could be y equals 1, and this could be y equals 2. And this curve is y equals f of x. So consider first the limit as x goes to 1 from the negative side. So what that's asking is, as we approach 1 from the negative side, the inputs are doing this, and what are the associated outputs doing? So you can find out just by going up to the curve and coming over. So as we approach 1 from the negative side, the outputs are approaching 2 on the y-axis from below. So if somebody asks, what is the limit as x goes to 1 from the negative side, the answer would be 2. If somebody asks, what happens as x approaches 1 from the positive side, now what you have to imagine are the inputs are creeping up on 1 from the positive side, and so what are the outputs doing? You can check with the curve. So as the inputs approach 1 from the positive side, the outputs are approaching 1, it looks like, kind of from both sides. So this is 1. Now, if you've studied the section of the book, you know that neither one of these facts has anything to do with the actual value of the function at 1, because the limit just has to do with what happens around 1, but not exactly at 1. So it happens that f of 1 is equal to 2, but that has nothing to do with these limits. So that's the material that you need to know to do this problem. And if you want to go through it more slowly, then you can go to the section of the book that describes one-sided limits. And so here you see x is approaching 2 from the negative side, and there's a long explanation with lots of examples showing you how that concept works. Okay, next problem. This is pretty much exactly the same as the previous problem. Is that right? Oh no, this is asking about continuity and limits. All right. So we haven't talked about continuity yet. So here's what continuity means. So if you look at sort of an ordinary curve, here we're talking about the concept of continuity. So let's say that this is pretty much a smooth curve, except that there's a little jump right here. So this is y equals f of x, and let's consider 2 points here. Actually, let me add a little twist. So let's say that there's also a jump there. Oh, sorry, I guess this is the notation I should use. Right. So let's consider these three inputs. Let's say they are A, B, and C. Okay. So what continuity means basically is that the value of the function is consistent with what the limit suggests the value of the function should be. So for example, here at A, if you look at the limit as x approaches A, it looks like the output is just going to be, I guess we need to make up a value here. So let's say that this is 1, and just for simplicity we'll also put that guy on the same level, and then let's put these 2 points down at the level of 1/2, and for simplicity let's move this output down to 1 also. Alright, so the limit as x approaches A for this curve. So as the inputs approach A, the output approaches 1. Now you can compare this to the actual value of the function at 1, at A, and so you can see that the actual value of the function at A is 1, and so this equality is true. So when this is true, as it is in this case, f of x is said to be continuous at A. So this is sort of the egg-headed symbolic definition. What it basically means is that the curve in this region, it can be drawn by a pen that's just left on the paper and never picked up. So it's just an unbroken line. In graphical terms, it just means an unbroken line. But in terms of the symbolism, it means that the output of the function at A is the same as the limit as x approaches A. So this particular curve is continuous at A, but look, it's discontinuous at B. Why? Because if you look at the limit as x approaches B, which remember has nothing to do with f of B, the limit as x approaches B is 1/2, because looking at inputs close to B, the output should be close to 1/2. So that's true. The limit has nothing to do with what happens at the actual limit point. So if you look at what f of B is 1, and so these things are different, and because they're not equal, we say that this function is discontinuous at B. So now consider this last case. I lost my B, I'll fix it. At this point C, you could ask the question, is it true that the limit as x approaches C of f of x is equal to f of C? So in a way this is kind of a trick question, because the limit as x approaches C does not even exist. And because we're still exploring this stuff maybe for the first time, you can ask yourself, why does the limit not exist? the limit doesn't exist because the left-sided limit is not the same as the right-sided limit. So that always has to be true for a limit to exist. So this is because the limit as x approaches c from the left is equal to 1/2, and this is not equal to the limit as x approaches c from the right. As x approaches c from the right, you get 1. So whenever there's a mismatch between the left and the right, you say that the limit does not exist. So then this equation can't possibly be true, and so this is another kind of discontinuity. So this function is also discontinuous at c. And functions will always be discontinuous at places where the limit fails to exist. So for example, if it had a vertical asymptote over here, that would also be another discontinuity because the limit doesn't exist at a vertical asymptote. And that would be true even if you had a point where the limit was infinity. Still false. I mean, it's still discontinuous here. And not only does the limit not exist, but the value of the function isn't even defined. So yeah, so that would be another way that it could be discontinuous. So if the function just weren't defined here at b, it would also be discontinuous at b. So if you would like to know more, you can read the section of the book that talks about that, which is this section 2.2, which everybody theoretically has read. Okay, so let's keep going. All right. Okay, so you should know enough to answer that problem with the things that we've already talked about so far. And same thing here. Oh, well, actually, we haven't talked about limits at infinity. But you should be able to tell what the limit as x approaches 0 is. And actually, this uses something called the squeeze theorem, which we've not talked about at all. So the right way to do this problem is to, let me just do a search here for squeeze. So is it in this section? I don't see it, so it might be in 2.3. So we're going to load that up. And let's look for squeeze here. Oops, yeah, here we go. So the right way to do this problem that we're looking at now is using the squeeze theorem. And so you can read this. Let me show you basically what's going on here for this one, and sorry again about the noise of the rain. So if you look at the expression that defines this function, it's given right here. It's x squared times sine of 7 pi x. So this curve is always bounded above by the parabola x squared. That's because this value sine just alternates between plus and minus 1. So the biggest it could possibly be is positive 1 times x squared. So x squared is sort of an upper bound. And then the lowest sign can be as negative 1. So negative x squared is a lower bound for where this function can go. So here we have a function that's squeezed between x squared on top and negative x squared on the bottom. And so the part of the book on the squeeze theorem explains that when that happens, the limit of the middle function has to be the same as the limit of the two squeezing functions. So in the case of this problem, the limit as x approaches 0 has to be 0, because The limit as x approaches 0 for x squared is 0. The limit as x approaches 0 for negative x squared is 0. And this function is pinched between them. And then we haven't talked about infinite limits, and this is not in our book. So for these two, just say that it doesn't exist. And that makes sense because you can see that it's not settling down to any value as we approach infinity, and it's not settling down to any value as we approach negative infinity. So neither one of those exist. All right, so now we're moving on to the part of the book that deals with the limit laws, which is 2.3. So you should read that section before you do these problems. So let me show you how this one works. Come on, thing. Right, and we have a new page. So we want the limit as x approaches negative 2 of 5t minus 9at plus 9a. So one thing to notice is that there is a letter in this expression which is not the variable a. A is a constant. And so the answer will involve a unless it cancels out. And so we should expect that to happen. So the answer will not be a number necessarily. So what the limit laws say is that the limit can come into this expression like this. So this becomes the limit as x goes to negative 2 of 5t minus the limit as x goes to negative 2 of 9at plus the limit as x goes to negative 2 of 9a. And so you can evaluate all of these separately. So which limit law is it that says you can do that? So the limit law that we're talking about now is, it must be for the sum, right? Where's that? Oh, here it is. Okay. So what we're talking about is the what they call the sum law for limits and the difference law for limits. So that's what we did just now, and then there's another law that says you can spit out constants. So let's do that. So this becomes the limit as, oh wait, sorry. So the 5 can come outside the limit, and this becomes 5 times the limit as x approaches negative 2 minus 9a, which is a constant, times the limit as x approaches negative 2 of t. And then there's no variable in this last part, it just is a constant. So for this last part, we're ready to use the constant law here, which is given right here. It says the limit as x approaches a for a constant function is just the constant. So for this part, the limit as x approaches negative 2 is just 9a, because there's no variable involved at all. So this is plus 9a. And now let's come back and do the rest. Oh, I forgot to write the t here. That was dumb. All right, so now we've got these limits right on the variable. This is just the limit as x goes to negative 2 of t. Oh gosh, and I've been making another mistake here. So the variable in this problem is t. I'm sorry. So all of these x's should be t's. If the video weren't so long, I would start over, but I've been talking for like quite a while now, so I'm just going to change these x's to t's. I'm very sorry. So all of these x's should be t's. T, 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 t. Sorry about that. So now we have the limit as t goes to negative 2 of t, and if you look at the limit law, this one, that's just saying that the limit is the limit of the variable is just the limit value. So this becomes 5 times negative 2 minus 9a times negative 2 plus 9a. So if you collect all this stuff, you get minus 10 and then you have plus 3 times 9a, and so let's just double check that that works. So this is 27a minus 10. Let's try it. Okay, good. Now I'm going to stop the video just because there's a slight chance that this thing is not working at all and I'm talking to myself. And maybe I'll pick up in another video.